start with the same example that we did last week. So there are like four people who are, let's say living in a building, and they are represented by this matrix, this transition, this diagram. Don't you remember this one? So you have Eva, Wong, Yumi, there's the names made up in the question, and Kim, right? Now, this is how they communicate with each other. They all speak different languages. So Yumi can communicate to Wong in her language, and Wong can communicate to Kimi in her language, and so is Eva and Wong. So Wong is the central point of contact. So in case Eva has to talk to Yumi, then it has to go via Wong. Right? So let's create a matrix of this diagram first. So we say, let's say my sender are the rows and receiver are the columns. So senders, again I say E, W, Y and K. And then you have E, W, Y and K. So they are the receivers here. Receivers are here. Now, wherever there is a direct connection, we write a 1 there. So Eva and Wong. So Eva and Wong, and obviously Wong and Eva. So Wong and Eva here 1. Right? Yumi and Wong. Yumi sender, receiver Wong. Yeah. And Wong and Yumi is a 1. Wong and Kim. Kim and Wong is a 1. And Wong and Kim is a 1. Yes? And rest everywhere it has to be a 0 because there is no direct communication. So I'll place a 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Is this matrix the right representation of this diagram? I need to see a nod yes or no like, right? Yeah? See, Wong to Wong is a 0. Obviously, that doesn't mean Wong cannot communicate to Wong. I can communicate to myself, but I won't speak, right? I'll think. This is about talking to each other. So that's why it's a 0. That makes sense. Eva to Yumi. They can't talk. It's a 0. So this is the right representation. I call this matrix as communication matrix and I name this matrix as C. This matrix is called one-step communication matrix. One step means we are on page 526. So this is one-step communication matrix. That means wherever there is a direct communication possible, just one step. Just one step. And these ones and zeros does not represent the number of steps. This is binary. Binary is 0 and 1. 0 is false, 1 is true. So what it actually means is that a 1 here means true. True for Yumi and Wong. So that means yes, Yumi and Wong can talk in one step. That's what it means. It doesn't mean the count. Okay, mind you. And wherever there is a 0 means a false. And exclude this, please. Don't consider this because Obviously, Eva is a 0. That doesn't mean that they can't communicate. That means it's the same people. There's no need for communication. Wong and Wong is a 0. Yumi and Yumi is a 0. Kim and Kim is a 0. So you ignore the leading diagonal. All good? So far, so good? Now, if I say that this is the communication matrix here, that's slightly incorrect, a statement. This statement tells me that, okay, if Kim wants to talk to Eva, it's a false. It's a 0. But that's not the case. She can talk. Kim can talk to Yumi via Wong. So first, she will talk to Wong, and then Wong passes the comms to Yumi. So how many steps are involved here? 2. So this one-step communication matrix is not giving us the full picture. So let's now try to see how do I create another matrix that gives me the communication links where there are 2 steps involved. So in order to do that, what I do is I square this matrix. So if you go to your CAS and if you put this matrix as matrix C or A or B, whatever, and you square that, you get something like this. Your C square will look something like this. So you've got E, W, Y, and K, E, W, Y, and K. So when you square it, it looks something like this. You'll have 1, 0, 1, 1, 0, 3, 0, 0, 1, 0, 1, 1, and 1, 0, 1, 1. This is how it's going to look. Now let's try to understand what this is. What this is. It's C squared. As in the first matrix, I will just ignore this. And I'll read the rest. And what you will see, the rest is still zeros and ones. And I as told you earlier, zeros and ones are just binaries, true or false. And this is a C squared. So this is a two-step comms matrix. So this matrix tells me where in this diagram 2 steps of communication is possible. So let's take the same example. Kim to Wong is first step and Wong to Yumi is second step. So that means between Kim and Yumi there is a 2-step link. Let's now try to find this here in matrix. Kim and Yumi. You got a true. So this true actually means, since this is a 2-step comms matrix, Kim and Yumi have a 2-step link between them. This won't be a 2 here. It will still be a 1, which tells me true. 2-step comms is a true between K and W, K and Y. Does that make sense? Yep. Wherever there are numbers more than 1, because since we're talking about binary language, the computer is binary, right? Zeros and ones. I call these numbers which are greater than 1 as redundant links, and I safely ignore them. And they are primarily around the leading diagonals. Leading diagonal, the other diagonal. So if you've got anything greater than 1 in your square matrix, then you safely ignore those numbers. I'm just concerned with zeros and ones here. All good? Make sense? Now, in this world, coming back to this world, how many total links now do I have? I had a set of direct links, 1-step links, and I have a set of few indirect links, the 2-step links. And suppose this diagram would have been even extended where probably a 3-step link would have been there. then would you have simply cubed it another. So you would have found a C3. That would have given you 3-step comms. But then in here it's not required because you haven't got anything more than 2 steps here. So I'm not going to C3. Now I need to know how many total com links are there. Total com links are there. So I've got a C, matrix C, which is 1 step, and a 2-step matrix. So I end up adding these two together. So far so good? With me, yes or no?
Yeah.
Let's add them now. Let's add C plus C square. So you know what you'll get? You will have E W Y K, E W Y K, and you'll have 1 1 1 1 1 3 1 1 1 1 1 1 and 1 1 1 1. I safely ignore this 3 because it's a redundant link. So what this tells me now? This matrix tells me that between Kim and Yumi, there is a 1. That means yes, they can talk. Either 1 step, directly or indirectly. That's about it. So, whenever you are establishing a direct communication link, you directly plug in a 1 where there is a direct connection. Rest are all zeros. That's 1 step. Wherever there are 2 steps, you square the same matrix, ignore the redundant links, and the 1 tells you 2-step comms is possible. And when I say, okay, give me the total, add both the matrices in, and you get the total set of comms.